Light, it bathes our world in brilliance. It reveals the vastness of the universe, but can we truly control it? Can we sculpt its path and tame its energy? I'm not just talking about simple mirrors or lenses, as useful as they are. Imagine the power to meticulously guide light, bending it precisely to our will. This extraordinary capability lies within the realm of photonic crystals. These are materials that seem to hold a special kind of scientific magic. They offer us a profoundly new way to interact with the very essence of light. Prepare to embark on a journey into their fascinating, luminous world. You might just be amazed by what we discover together. Let's pause and think about light for a moment. This fundamental cosmic messenger. It races across the immense distances of space, carrying information and energy. It exhibits a curious dual nature, behaving like a continuous wave. Yet it also acts as if it's made of discrete particles, tiny packets of energy. These particles are what physicists call photons, little bullets of light. For centuries, humanity has guided light using simple tools like polished glass. Lenses have allowed us to peer into the microscopic or gaze at distant galaxies. But photonic crystals operate on a different level, a radically more intricate one. What if you could construct an incredibly detailed maze, specifically designed for light? A structure so precise, so perfectly ordered that light has no choice but to follow its rules. That, in essence, is what a photonic crystal accomplishes. You can think of them as nature's own traffic signals, directing the flow of photons. Or increasingly, they are structures meticulously designed and fabricated by human ingenuity, engineered with an almost unbelievable degree of precision, a testament to our skill. These structures exist at scales almost unimaginably small, the nanoscale, and they empower us to perform feats with light that once seemed like pure science fiction. Why is this field of study so captivating, so profoundly important for our future? Because when you control light, you are, in effect, controlling energy and information. This mastery opens wide the doors to a dazzling array of new technologies. Imagine communication systems that are orders of magnitude faster than today. Consider sources of energy that are far more efficient, harvesting light with greater success. Or even new imaging techniques that allow us to see the previously invisible. Photonic crystals are far more than just scientifically curious materials. They are powerful tools, keys to unlocking new frontiers in science and technology. So, what are these remarkable photonic crystals actually made of? How are they constructed? Imagine a perfectly repeating pattern, an intricate microscopic lattice. Think of the delicate iridescent scales on a butterfly's wing shimmering with color. Or picture the ordered structure of a precious opal, its colors shifting with every glance. But these engineered crystals are structured on a much smaller scale. Nanoscale small. They're typically composed of arrangements of at least 2 different materials. These materials must interact with light in distinctly different ways, affecting its speed. They alternate in a precise, periodic fashion, like a tiny 3-dimensional checkerboard. This meticulously ordered regular structure is the absolute secret to their power. How does this carefully crafted structure manage to exert such control over light? The answer lies in the wave-like nature of light itself. Remember those light waves? When light, as an electromagnetic wave, enters the photonic crystal, it encounters these patterns. The waves begin to bounce, to scatter off the interfaces between the different materials. Crucially, these scattered waves interfere with each other, constructively or destructively. Some specific light waves or colors find that their path through the crystal is clear. Other waves, however, are strongly reflected. Their propagation is effectively forbidden. It's like a highly selective bouncer at an exclusive club, but operating for photons. Only certain colors, or more accurately, wavelengths of light, are granted entry. This selective interaction with light leads to a truly fascinating phenomenon. It's known as a photonic band gap. That might sound like a complex term, but the underlying idea is elegantly simple and incredibly powerful. A photonic band gap is essentially a range of light frequencies or energies. These specific frequencies are unable to travel through the crystal structure. Think of it as a forbidden zone, an energy barrier that light of that color cannot cross. If a photon possesses an energy falling within this wrong range, it is blocked. It simply cannot propagate or exist comfortably inside that specific crystal structure. This photonic band gap is the very heart of a photonic crystal's unique power. Let's use an analogy. Picture a vast, perfectly ordered forest planted by a cosmic gardener. The trees are arranged in incredibly neat rows and precise columns. Now imagine trying to roll a ball through this meticulously structured woodland. Some paths directly between the rows might be surprisingly easy, allowing straight passage. Other attempted paths, however, would be impossible. The ball would inevitably hit a tree. Photonic crystals act in a very similar manner, but for the waves of light. They create allowed pathways and strictly forbidden pathways for photons. By carefully designing the forest, the crystal's structure, we design light's journey. This is engineering at its most fundamental, manipulating the very behavior of light. Now, this compelling idea of controlling the movement of tiny particles isn't entirely without precedent. We as humans have become quite adept at doing something very similar with electrons. Electrons, those tiny charged particles, are the tireless workhorses of our modern digital world. They are managed and directed within special materials known as semiconductors. Think of silicon chips, the intricate brains residing at the heart of your computer or smartphone. These remarkable chips meticulously control the flow and behavior of electrons. Photonic crystals, in a beautifully analogous way, aim to do for photons what semiconductors achieve for electrons. It's a grand parallel in physics, a stunning symmetry in how we manipulate fundamental entities. Semiconductors, the bedrock of our electronic age, also possess a critical feature. This feature is known as an electronic band gap, a concept vital to their function. It represents a specific range of energy levels that electrons are forbidden to occupy. This very property allows us to construct microscopic switches, the essential transistors. These transistors can turn electrical currents on and off with incredible speed and precision. This ability to control electron flow forms the basis of all digital computation. This mastery over electrons utterly transformed our world in just a few decades, from colossal, room-sized computers to the sleek, powerful phone resting in your pocket. It was without any shadow of a doubt a true technological revolution. Then, in the pivotal year of 1987, a new luminous vision began to emerge. Two brilliant physicists working independently of each other conceived a groundbreaking idea. Their names were Sergey John and Eli Yablonovich, pioneers in this nascent field. They posed a profound question. Could we create a similar kind of band gap, but for light? Could we potentially control photons with the same degree of precision we had for electrons? Their crucial theoretical work laid the essential groundwork for this new scientific endeavor. It demonstrated through rigorous calculation and insight that yes, such control was indeed possible. This marked the true birth of photonic crystals as a distinct and exciting field of research. Their collective insight was not just an incremental step, it was profoundly game-changing. If semiconductors had gifted us the age of electronics with all its wonders, then photonic crystals held the tantalizing promise of ushering in an age of photonics. This would mean creating circuits that utilize light itself instead of electricity as the messenger. Imagine photons, particles of light, zipping through incredibly tiny engineered channels on a chip. These light particles would carry vast amounts of information at almost unimaginable speeds. This wasn't merely proposing a minor improvement to existing optical technologies, it represented an entirely new paradigm, a whole new way of thinking about and manipulating light. The impact of their work continues to resonate through labs and industries worldwide. So, where can we observe the impact of these incredible photonic crystals in our world today? You might be surprised. Take a look at the modern LED's light-emitting diodes. Many of these ubiquitous light sources are now significantly brighter and more energy efficient. This improvement is often thanks to the clever integration of photonic crystal structures. The crystals are designed to help guide the light, coaxing it out of the LED material. They effectively prevent the precious light from being trapped and wasted inside. This means more useful light is produced for less electrical energy consumed. That's smart science. It's a seemingly simple application, yet it carries a substantial global impact, saving considerable amounts of energy and lighting our world more effectively and beautifully. Now let's consider optical fibers, the slender threads that form the backbone of the internet. These are typically tiny strands of ultra-pure glass carrying data as rapid pulses of light. Photonic crystal fibers represent a new advanced generation of this vital technology. They possess the remarkable ability to guide light even more effectively than traditional fibers. They can do so with significantly less loss of signal strength over long distances. They can even guide light around tight corners where older fiber designs would leak light and fail. This translates directly into faster data transmission rates and more reliable global connections. They are constantly pushing the known boundaries of communication technology. All of this progress is made possible by these tiny, meticulously structured optical marvels. And the range of applications certainly doesn't stop with just lighting and communication. Consider the domain of sensors, devices that detect changes in their surroundings. Photonic crystals can be engineered to be incredibly sensitive, highly responsive detectors. Even minuscule changes in their immediate environment can subtly alter how light passes through them. Imagine a sensor capable of detecting the presence of a single specific molecule or a tiny virus. This capability could completely revolutionize medical diagnostics, making them faster and more precise. Or it could help us monitor environmental pollution with an astonishing new level of accuracy. Photonic crystals allow us to sense and perceive the world in ways we previously couldn't. Light guided by these structures becomes our finest, most delicate probe. What does the future hold for photonic crystals? It appears undeniably dazzling and full of potential. Scientists and engineers around the globe dream of building practical optical computers. These machines would use photons, not electrons, for computation, a radical shift. They could potentially be much faster and perhaps more energy efficient than current computers. We might also see more efficient solar cells designed to capture more of the sun's abundant energy. Perhaps further down the line, even exotic metamaterials that can bend light in truly extraordinary ways. Think of applications straight from science fiction, like advanced cloaking devices. The journey of discovery in the realm of photonic crystals is far from reaching its end. These crystals are more than just interesting materials, they are a profound testament. They stand as a testament to our enduring human ability to understand and ultimately to shape the universe around us.